Okay, so the first part that we're going to go over is diffusion. So diffusion is Brownian movement that you would have. So this is molecular diffusion, is the migration of a solute from a region of higher concentration to a region of lower concentration due to kinetic activity of a molecule. So this is random motion. So how does this look? You know, you guys have all done this before. You've got a concentration, like a beaker here. At this time, the concentration on this side is 0. On this side, the concentration is 100%. So I can equals 1. So let's just say it's 1. Just to be like a percentage, it's 1. It's everything. Then after with some intermediate time, the solute starts to diffuse across, over into this side. And then at some longer time, the concentration on this half and the concentration on this half are equal. They're equal to the original concentration divided by 2, so the C naught over 2, so that's C naught, that's what that is. And then you have the same concentration over thing. So what's going on there is Brownian motion, where every molecule is just kinetically moving in whatever direction, and so they just move in there. And then eventually they move over to this side because there's lower concentrations on this side, so they're not bumping into each other, and then they'll come into equilibrium with each other. And so this is this is not reversible. It's you would have to actually put some energy into this. This is a random type of situation with the Brownian motion. This is not something that this is not reversible unless we do something like we put a force into it or something. So this is not reversible. So the vibrating molecules move in an erratic fashion. That's what's going on here. And they'll randomly bind themselves to diffuse altogether. Although the motion is random, the net result of the molecules move from higher concentrations to lower concentrations because now they're bumping into each other. Over here they're not bumping in, so they can go further distance. And then once the Brownian motion has all gone into there, we get them equalizing. So this is the basic concept of diffusion. So why is diffusion important? Okay, so hold on a second. Okay, so why is diffusion important? Well, it's important for a couple reasons. So why important? Why important? Well, at a micro scale, it is a very fast process that generally influences mixing of dissolved contaminants, especially in a dual porosity media. Okay, so what does that mean? So on a micro scale, so we're talking what's going on with inside of the aquifer, inside of the things, inside of those areas. What you'll have is this is very fast, so the process of diffusion is happening very quickly. It's a mixing of the solutes, so it's a mixing of dissolved contaminants. Okay, and then when I said a dual porosity media, so why is it important? The micro scale. It's very fast process, which influences mixing. So we're getting our mixing of dissolved contaminants, which is really important because we're going to have to see them move, especially in a dual porosity media. Dual porosity media. So what does a dual porosity media mean? So this could be something like soil aggregates. Fractured clay. So where you have two porosities. Okay, so if you have like a fractured clay here, and this happens around these parts here and in different parts of the country, and you get soil aggregates. Soil aggregates is actually really common, especially near the soil surface. And so if you've ever played in the dirt, you'll get these little aggregates. So, like if you break up dirt, it'll form like clumps. Well, those are called aggregates, okay? And, because like if you play in the dirt and all of a sudden it's not all uniform in their size and shape, like sand does. But if they form any sort of aggregates, they'll form these naturally forming little clumps. Well, with inside of those little clumps, you can get these aggregated soils. You can get like say you have a bunch of them, they're aggregates and stuff like that. Well, the groundwater flow, I'll try to use two different colors, is going through like this. Well, what it's doing is as the contaminant's going in here, it's diffusing into these aggregates. So these could be clay-filled particles into there. So it's diffusing in, and then it's also diffusing out. So it's going in and out of these little aggregates inside of here. So flow is mainly through the macropores. So this is a macropore. So what you can see is that as contaminants are moving, they're going to be moving in the fastest flowing water that's in there. So these are the macropores in between these soil aggregates. So you can get, and we'll talk about what this looks like when we do transport. The flow is most of it, but because of diffusion, solutes move slower than the groundwater velocity. So even though they're 100% dissolved inside of the water, so say it's a salt, I'm going to use salt as our conservative tracer and our conservative piece. Because of that, what will happen, it will slowly move in and slowly move out of these aggregates and stuff like that into there. And so you'll get actually moving it slower than water. So you can get these fast flowing things where you can get it coming in really, really fast, and that this slows it down compared to the groundwater velocity. Diffusion into macropores or into dead-end pores, so we're going to do diffusion into there, can happen this way. So it's mainly through the macropore, so these are this right here. This is our macropore, and then these are our little aggregates here. So these are our little soil aggregates. Into there. And so the flow is mainly through this micropore, but because of diffusion, you can get the contaminants moving into these different pores and stuff like that. So that's one way that can happen. Now, with inside of a fractured rock, so a fractured clay, so if you've got fractured rock or a clay, which can happen, you'll have a fracture here. I should make it so smooth, but it'll be a fracture here. And again, our groundwater flow will mostly be fast flowing through the fracture. So this is flow through the fracture. And then due to what's called matrix diffusion, you can get the contaminant then slowly, more here than here than here. The result of the retardation is you're going to get this what's called matrix diffusion. So this is the matrix, is the part outside of the fractured rock. This is the matrix. And you can get the solute diffusing into that clay, into there, or if it's a rock, or into there. And so what happens is that the result in retardation of a solute, so where this results in, so this results in retardation of the solute relative to flow velocity in the fractures of the macropores. Okay, so this is what happens. So this results in retardation of the solute in regards to the velocity in the fractures. Fractures or macro pores. Okay. So on a small scale, this is what happens inside of a system. But at a mega scale, this can also happen. So what happens at a mega scale, diffusion can be very slow. So at the micro scale, it's very, very fast. At the mega scale, so when I'm talking mega scale, I'm talking like whole field sites and stuff like that out there. So at the larger scale, so we're going to say at mega scale, diffusion can be very slow. So this can be very slow. And diffusion-dominated deposits can provide reliable containment of waste. Okay, so at the macro scale is very slow, and diffusion-dominated deposits can provide reliable containment of wastes. So what happens is that at the macro scale, because diffusion is so slow at the really big scale, that you really don't even have to consider this. Now on intermediate scale, so like a field site kind of scale, so this is like, you know, whole state, a large, really large scale. At the intermediate scale, so this can vary widely, okay? So take like in this particular area, we have our ground surface here. So we got our little grass and stuff like that happens over here. We got our person standing here, okay? So we got a little person standing in here. Well, in this particular area, what is the geology like? Well, one of the things that you'll find out is, if you don't know that much about glacial geology, is that you'll get tons of these like clay lenses that'll happen. That will be in here. So you'll have a sand here, and you'll have a clay lens. And even in a sandy aquifer, you can get these clay lenses because of, you know, the geology that's here. Because of the glaciers that are coming in, you know, it may be a really flat landscape here, but once you start drilling into this landscape, it can vary 3 feet from each other. You can get differences in the geology that occurs at a site. And so what you can have is, as your contaminant is moving in, and you've got your contaminant over here, moving into here, it's going to start to diffuse into these clay lenses, and then it can diffuse out of those clay lenses, and so you can get that kind of thing happening there. So the initial migration of contaminants will be retarded by diffusion into the clay lenses, and since the ability of clay to absorb is generally greater than sand, so the clay is much greater than sand for absorption. So clay lenses are much greater than that. What will happen is these clay lenses that are found within inside of the geology around here, it'll diffuse into there, and it'll slowly diffuse out. And this is part of the problem with like pump and treat, is that we'll pump the contaminants out really fast, but then some of it has diffused into these clay lenses and other areas like that. So remediation of aquifers can be largely controlled by the diffusion that has occurred into these clay lenses, and has to desorb, and it has to diffuse out of the clay. And this could be a very long process, especially with pump and treat. So there's been some spectacular where they looked at a site and they go, oh yeah, we cleaned it all up because we can't pump anything more, and then all of a sudden they turn off the pumps, and then they look at it, and then the contaminant is now diffused back into the groundwater into there. So on the very micro scale, you can get these kind of processes happening at the very, very micro, what's happening at the grain level. But then at the mega scale, like, you know, whole cities or something like that, it's really slow. We don't usually consider it. But at intermediate scales, where we're looking at field sites, this is actually an important process that occurs. As well, diffusion can be significant in transport of a wide range of geological materials and manufactured materials. So let's look at, like, say, a landfill. An example is for diffusion through an engineered lining. So, because this doesn't just have to be from geology, you know, or something natural, but the diffusion through an engineered liner. So where do we see engineered liners? At landfills. So landfills will have what's called an engineered liner. So what this is generally what happens is you can have this is a compacted clay. You know, the hydraulic conductivity could be here about 10 to the minus 8 to 10 to the minus 9 meters per second. Into there, and usually these are greater than 1 or less than 1 meter in size, and so you'll have the leachate up here coming through the landfill. So a leachate, that's where the groundwater or the water goes through the landfill and picks up and dissolves all of the stuff that's in that mixed stuff of a landfill. That leachate will come to this compacted clay, and then they either pump it off, but because of this compacted clay, there's approximately, so they design these things so that if there is no pumping, there is nothing, that this leachate just sits right on this clay. If it's less than 1 meter of this really highly compacted clay, approximately 5 years for a non-reactive solute to penetrate this clay. So approximately 5 years of it just sitting here before it can get through this 1 meter of clay. Then what they do is they put a layer down here underneath this clay. They will put a engineered liner right there. So this is usually like a high density polyethylene. So the plastic, high density polyethylene, has such a large or small diffusion, and so we usually look at diffusion, we usually use it as D star is our main thing we look at for diffusion, is really, really low. And so whatever is coming out of the clay will hit this lens, and then that'll hold it up into there. And then usually underneath this you put a granular substance. So this will have a very low D star, and then here you'll have all of this dots and stuff like that that happened into there. And you can get that diffusion occurring there, okay? So this can be a granular deposit, and then they can drain off of this. So you're trying to contain it so that it stays up into this area, and it'll take a long time. And this 5 years is things like that are dissolved into the system. So this would be like salts into the system, into there. You can get false contamination of groundwater sampling wells due to diffusion through the casing. So what can happen is generally with low density polyethylene, so like say you have a well, and here's your screen, and here's your contaminant up in here. You have your ground up in here, and you got your water table here, and here's your contaminant. If this is a PVC pipe and stuff like that, sometimes what can happen is you can actually get diffusion through this plastic, through the PVC pipe, or through the actual through the actual material here. So like if you have a well sampler and stuff like that, plastics are not completely impervious to diffusion. So what can happen is it just may be slow, but you can get contaminants like falsely being where the well screen is, actually coming in through there. And so that can happen. And so generally low density polyethylenes like HDPE, Tygon, Teflon tend to have higher diffusions than say high density polyethylenes or PVC. So depending on what the material is here, it can allow some of that contaminants to diffuse in there. So we try to use, so if you're using sampling tubes and stuff like that, you can actually get contaminants diffusing across plastics. So that's what it's saying. And I'm saying that high density polyethylene and PVC are better than say low density polyethylenes, and they can absorb onto contaminants, and contaminants can absorb into them. So when we're talking about microplastics, y'all that are doing microplastics for your research, you have to think about diffusion of the contaminant into plastic microparticles, and then those particles could move and spread your contamination over into there. So that is it for diffusion for right now.